Hello, and welcome to Chapter 1, the first lecture in Psych 92 Research Methods. As I told you guys in the syllabus, we're using the third version of this book, but the slides, as you can see, come from the second edition because that's the one I used to begin with when I created the slideshows. In this course, we will have about half the time on lecture material and the other half doing what would have been in-class stuff and a lab type experience where we will be building towards writing a final manuscript based on an experiment. In the normal class on ground, what you would normally have is that you would get together about halfway through the semester as a group of 4 or so, and you guys would choose an article, and the group would pick one, and then you would end up changing it in a way that makes it its own new experiment and running it in front of the class with your other classmates as your participants. But because we are limited to an online format, that changes slightly, and we will end up all reading the same article, seed article as we call it, because it's the seed from which your experiment grows, and you will get a chance to change the variables as a little bit or a little more, and I will provide a data set, and you will be able to essentially, hypothetically, run your own experiments, or at least pretend to run your own experiments, and that will be what you're writing about. But let's get back to this. I'm going to go ahead and put this in presentation mode. And here we see, we will see that each chapter has its own set of learning objectives that I have included in the slides because I want to give you guys a good idea of how or what to look for when we go through the chapters, sort of to keep that in the forefront of your brain. So the first learning objective is that we are going to articulate, me specifically, how the roles of consumers and producers of research are similar and how they differ. And I would like to point out as we're going through this that to be a good producer and consumer of research, it doesn't necessarily just need to be about psychology. Obviously, the producer part, which entails understanding the variables, picking the right research design, and things such as having the right definitions and the right statistical analysis, all of that makes you a good producer of research. To be a good consumer of research, again, it doesn't have to be specific towards psychology. We can think of just general everyday consumerism, market research, and things like that. So I'll explain how they're similar, how they differ, and how to be one, you kind of have to be both, but the other one, you don't. Now, that sounds a little ominous, but don't worry, I will let you know what I mean by that. I will also explain how theories and data interact together to form what we call empirical inquiry. So one of the things that we talk about, and this chapter kind of gets into the idea of sources of information and why we can trust certain ones. In chapter 2, we go a little further as to say why we can't trust other ones, but we'll get to that when the time is right. But one of the reasons is that scientists take into account all of the information that they can get. This is what we mean by empirical inquiry. You're not just basing it off that one time you did something and it worked or didn't work. As a scientist, we take into account all the information, past research, anything that we can find. So I'll talk about how they interact and how scientists are empiricists. Third one says to identify examples of basic and applied research and describe the interactions between the two kinds of research. There's actually a third kind which kind of bridges the gap between them, but I will get into the ideas of what is basic research and how is it conducted, when is it conducted, and when do we specifically apply something to it or apply it to something. Number 4, describe how the peer review process affects communication of scientific ideas. Well, one of the reasons that we can trust scientific literature is because of the process that it goes through in order to even be published. Now, this is not so simple as taking your manuscript to a publisher and saying, I did it, I got a good result, here, publish this. It's not that simple. There's editors and there's peer reviewers, which means that experts look over your manuscript and make sure that everything is done in the best possible way. And only after it's gone through that approval process, which I'll go over, then you can actually publish it. So it's not like you can just print something and get away with it if it's not very good or if the data's made up or something like that. I will give examples of ways that researchers dig deeper, how they don't just accept one bad study and scrap their ideas, and how they don't just take one good study and say, oh, I'm done, I got this, next. They actually spend quite a lot of time in one area or one topic, but they progress the science as they do it. So I'll get into that. Finally, I will describe the differences between information that comes from empirical journals, that is trusted and cited, and doesn't just give that study's information, but gives information found from studies before it on the same subject. In the popular journalism, they can be accurate. They can give you the same stuff you get in journal articles, but most of the time that doesn't happen. And sometimes it can really be a game of telephone. Is the information relevant? Is the journalist going to want to change it to make it sound sexier or more interesting? Or are they not really going to care about it, so they don't really tell you everything? There's a lot of different ways this can go. So I'll describe the goals of each format and give examples of ways that journalists can do better and write better stories about scientific news. So in this chapter, we have research producers and research consumers for the first part, and then we'll talk about how scientists approach their work. So what does it mean to be a good producer of research? So I touched upon this a couple minutes ago, and really what it means is that you have a good knowledge base of how to make your study the best possible study it can be. So that means knowing the statistics. It means understanding the variables and how to separate groups, how many people per group that you need, what statistical analysis to use, what type of study you're running. We're going to hear terms like independent groups or within groups, factorial, multifactorial, simple correlation versus experiment versus surveys. So knowing all of those things and which is the best method going forward, you need to have these skills in order to be a good producer of research. So this is what we're going to try to build throughout this course. To be a good producer of research and understand what's going on with the studies and with all of these variables, you also need to be a good consumer of research. You need to understand things from a scientific point of view. To be a good consumer of research, it means to look through the literature and know what's relevant and what is not, and, to do your homework, to do your research on things. Do you have to be a good producer of research to be a good consumer of research? No. To be a good producer, you do need to be a good consumer. But to be a good consumer, you don't necessarily need to know variables and statistics and all of that. And you just need to know what to believe, what not to believe based on the sources of information. And this will really help you not just in this class, but well beyond. In life, for the rest of your life. So let's get into that. Research producers and research consumers. So why the producer role is important. I already pointed this out in order to give you an idea before we got into this. To be a good producer, especially for this class, if you're going to be essentially conducting your own study, kind of hypothetical, you're going to need to know and understand how the original study was conducted and how you can change it to sort of give it your own new flair. The producer role is important because a good producer of research is one that makes sure to be as thorough as possible and to make sure they have enough subjects, to make sure that the definitions are very specific and that you're measuring exactly what you're intending to measure. The consumer role, though, is also important. What are the benefits of being a good consumer, and why is the consumer role important? Well, let's step away from the psychology lens for a second. We'll come back, I promise. And let's take a look at this. So if you're going to buy a car, are you going to go to the lot at CarMax or wherever you're going and just, when the car salesman comes up to you, are you going to just accept the first offer they give because, hey, it's a shiny new car and this person knows what they're talking about, so, why wouldn't they start with the best offer? Because the world doesn't necessarily work that way. A lot of times they work on commission, and they just want to give you something expensive so they get a higher paycheck. If you're actually going to do your part in car shopping and you want to make sure that you're not taken for a ride, what are you going to do? Well, one of the things I would suggest is look up the cars and see which maybe brand is in your price range and which features the cars come with. Maybe what's the best gas mileage, what's the lowest price out the door, the best warranty, right? All of these things that you want to find out. So you're going to do your homework and you're going to look all this stuff up. That's what being a good consumer is. It's knowing that you're not getting a lemon, knowing you're not going to pay $3,000, $4,000, $10,000 more than you should be for the same car you could get somewhere else, or that the warranty is horrible. Being a good consumer means taking all of the evidence that you can, all of the websites, all of the information, and making an informed decision based on these things. It doesn't have to be a car. It could be a restaurant that you're getting the best price for your money and the best quality of food. It could be a vacuum cleaner. It could be anything. Now, to step back into the realm of psychology, if you look at the pictures underneath, what you see is a man with electrodes, sort of an electro net, hairnet on his head, which is measuring most likely what we call EEG waves. It's measuring your brain firing, your neurons firing patterns. And this could be useful in sleep studies to see if people's sleep could be corrected if it's not working so well, and other areas of cognitive function. On the right, you see a man in a wheelchair who is being shown a tablet and trying to push down on the tablet. So being a good consumer means maybe finding out which chairs are compatible with this technology. If this tablet is good, to be able to help this person control the wheelchair, maybe get on the internet, turn on TV, and other things that may be beneficial in his life. Again, not just going with the first thing you see, but being a good consumer of research, knowing what's truthful, knowing what's not fake news. That phrase is thrown around a lot these last 4 years. And understanding that the information you're getting is correct and you're making the best possible decision. So, to be a good producer of research is also to be a good consumer. You don't have to be a producer to be a good consumer, though. So, why the consumer role is important? Well, when we teach psychology classes, when you take psychology classes, the proof that we have that theories are valid and valuable and information that we learned is printable is because it's based on studies. We use these studies to drive home points of the lesson. I'm going to talk about studies that have been done that were beneficial for research methods. In biological psychology, we look at studies of the brain to find out that certain parts of the brain have certain functions. These studies that have been shown have driven home the point of the lesson and backed up the theories that we teach. When you're looking at printed or online news stories and they're based on the research, the researcher or the research paper is cited, the actual statistics are provided, then you know as a consumer, it came from that peer-reviewed process that we'll talk about more later, and this is information you can trust. When you get something off of a YouTube video, sometimes they can be trusted if they're based on the actual research and it's cited. If not, then you got to take things with a grain of salt. It's all about critical thinking to be a good consumer of research. And for your future career, I'm assuming the majority of you, your major is psychology. Most people's are in Psych 92. And so let's say that for your career in psychology, you want to be a therapist. You want to work with people on the autism spectrum, help people with brain trauma. Well, when they're getting help rehabilitating or functioning, the things that are done, therapies and the like, are done using what we call evidence-based treatments. So what does that mean? Evidence-based means it's a treatment that has been shown, the evidence has been provided in the form of studies and experiments that these techniques, these drugs or medications work to be able to help because they have been shown time and again in experiments through research. So the therapies that we may use in clinical psychology or techniques we may use in training people with Alzheimer's disease or people on the autism spectrum can be supported because they have been shown to be effective in trials, in experiments. I've provided an example that says evidence based on scientific research shows that aerobic exercise can be an effective treatment for mild to moderate depression. Now, we're not talking about suicidal thoughts, pit of despair, major depressive disorder, but for mild to moderate depression, studies have shown that aerobic exercise can be effective. Does that mean that we should just forget any antidepressants and forget cognitive behavioral therapy? No, it just means that if you're feeling a little bit on the depressed side, maybe not enough for a doctor to prescribe medication, try aerobic exercise. And maybe you can try it in addition to therapy and or medication. So this is for mild to moderate depression. One of the things that we learn in biological psychology, if you took Psych 2, is that one of the biological symptoms of depression is a lack of serotonin. And one of the things that aerobic exercise can do is it can cause a little sort of ramp up, a little extra serotonin to come out of that. So you can see where it might fit in. You can see why the consumer role is important. So the benefits of being consumer, this is the part where I'd ask you guys, what do you gain by being a critical consumer of information? Knowing that your information is, yes, I'll answer for you because I'm the only one talking, that you know your information, if it's sourced, if it's from the scientific journals, if it's been vetted properly with a rigorous process, that information can be believed and can be trusted. And you know, using critical thinking skills, that what might be misleading and what might be something that you can really count on to know what's best for yourself, your family, friends, right? Things like that. So again, this is really important information for this course, but it will really help you for the rest of your life. Now let's get into scientists and how they approach their work. First of all, again, I said scientists are empiricists, which means they don't just take one thing one statement, one personal fact that maybe they witnessed themselves, and then just try to report it. They take literature reviews, so they look on the topic of their experiments or the topic of their theories, and they look and see what's already been done. They take that information, they base their hypotheses, their theories, their information on a lot of that. So they're taking in as much information as possible to make an informed decision, much like a consumer of research. Scientists then test their theories. We're going to talk about the theory data cycle, which goes from a theory, a sort of integrated set of principles that guides the research, into a design and then into something testable that they can actually collect data on. So we'll go through the theory data cycle. We talked a little about basic and applied ideas. When you first have a theory, before you've done any research to see if your theory is valid, that is what we would call a basic problem. You first have to experiment to see if it even works before you can get to how to apply it to something specific. So when we apply it, then you're taking that theory and you're applying it to something very specific. So the basic problem is a very broad, general way of conducting research, and eventually the applied one is a very specific way. So we'll get to that. Again, scientists dig deeper, which means that they're not just happy with one good result, and they're also not just going to quit based on one bad result. They dig deeper by looking more and more into it, and I will go over that. Of course, they make it public, so we'll go over the publication process, and then they talk to the world, from journals to journalism, and how much of a slippery slope that just might be. Stay tuned. So as I said, scientists are empiricists, and empiricism, which is also sometimes called the empirical method, or more often it's referred to as empirical research, shows that these people base their conclusions on evidence from all the senses, not just one or two, but all five senses, or instruments that can help them. They observe these things in a very careful manner, and again, it's not just limited to one or two cases. Many participants, many subjects, and based on a heap of evidence. So there's an example that I use for this class throughout the class that I start in chapter 1, so you're going to hear it a lot, and hopefully the more I repeat it, the more it is going to sort of make sense and really stick with you as we go through this class. So if we wanted to ask a question based on empiricism, we can ask this question as an example. How do we know that studying helps a person to do better in class? Well, it could simply be that you've always heard that. From elementary school, through definitely middle school and high school, and of course now at the college level, you have heard that studying, if you study and do your homework and you study, you'll do better in your classes. Well, we can't just say that we know that because that's what we've always heard our whole life. That's not part of empiricism. We need some sort of experiment, observation, to show that studying actually helps. I'm not just going to take somebody's word for it. As a scientist, I want to find out on my own. So we can devise an experiment to do this, and it's actually fairly easy. I'm not going to go through the ins and outs of everything that we have to do, as that will become clear as we use this example throughout the course. But to give you the main idea of how we would do it, and then sort of throw that into that theory data cycle. So let's say that we want to know, or we want to make a theory. We've always heard this. There may have been times you yourself have studied and did better in a class, and other times where you didn't study as hard and you didn't do as well in the class. But again, you can't just base this on your own information. You can base your theory on that, but we want to be empirical. So we can devise an experiment to do this. How do we do that? Let's make it as simple as possible. You're welcome, at least right now. So If you guys read the syllabus, and I really hope you did, and Snoop Dogg said so too, so you don't have to listen to me, but come on, you gotta listen to Snoop. So, in the syllabus, it talks about the appropriate amount of studying. In a normal 3-unit class, there is something called the Carnegie unit, which I included in the syllabus, that states for every hour spent in class, in lecture, you spend about 2 hours studying the material outside of class. So I know this is a 5-unit class. It's kind of split up into half lecture and half lab-based stuff towards writing your paper and understanding. So we'll just say it's about 2.5 to 3 hours of lecture each week, which makes it about 5-6 hours of studying according to that Carnegie unit. So what we can do is I can split the class up into 2 groups. A control group, which gets no manipulation. And if you don't know what that means yet, that's okay, because that's coming up in chapter 3 and beyond. And an experimental group that does do the studying. So half of the class will be separated randomly into the control group. Everybody listens to this lecture and follows along. And, you could take notes, I guess, while you're listening and watching this video, but 0 hours outside of that. So no reading the book, no studying notes, no going over a study guide or anything like that. And just this. The other group is going to be according to the Carnegie unit. So they also watch these videos for chapters 1, 2, 3, and 5. Let's say it's just for the first exam. And then they go and study 6 hours a week outside of class. So they read the book. Maybe they highlight, maybe they make flashcards, read study guides, take notes and go over those notes for 6 hours a week. And then at the end of 4 weeks or 5 weeks, you're all going to take the exam, and everybody takes the same exam, right? And what we would do is take the group that doesn't study and average all their scores together for one group mean, take all the people that do study and average all their scores together for another group mean, and we can figure out if the scores are different enough from each other. So this leads into our theory data cycle. The theory here would be that studying helps you to do better in class. So we start with a theory, and this could be, broadly defined. What does that mean to do better in class? Can you actually specifically test doing better in class? No, you got to make it a little more specific and testable. So the theory that people who study do better in school or do better in class can lead the researcher to pose particular research questions. And these research questions can be, if you study, do you get better grades? This can lead to an appropriate research design. And within the context of the design, as we go down, researchers formulate a hypothesis or hypotheses. The meaning of the word hypothesis is a testable prediction that essentially leads to your prediction. It leads to your, supports your theory. In this case, I gave the research design. One group was going to study 0 hours besides this lecture or these lectures. The other group, 6 hours. And so we can formulate our hypothesis. Based on the theory, studying helps you do better in class. How can we apply this to the class? Well, there are different ways that we assess grading in the class. The one that is obviously the biggest, besides the paper at the end, based on the lectures, it's the exams. So the hypothesis here, based on this research design, is our testable prediction. We have one group that studies 0 hours. We have one group that studies 6 hours. Our hypothesis is our testable prediction. If we have these two groups and they each take the exams, or everybody takes the exam, we would predict that those that studied 6 hours a week would score higher on the exam, get a higher score overall, average, than those that did not study in the control group. Then we can have you guys take your exams and we collect the data. And it can go in one of two ways. The data can support and strengthen the theory. So in this case, we see that on average, let's say the group that studies gets, 40 out of 50. No, I don't want to scare you. Your first exam, all of your exams are out of 40 points, not 50, but this is just hypothetical. So 40 out of 50 for the first exam from the experimental group that studies 6 hours, and about 30, maybe 29 and a half for the ones that don't study. This would support the theory. Are we done? Is that it? No, that is not it, because even if we get a really good outcome that we predicted and the statistics back it up, all that tells us is that it worked in our class with you guys. Does that mean it's going to work for another Psych 92 class at ELAC? Does that mean it's going to work for the theater arts class at ELAC? Or does it mean it's going to work for a class at West LA, in a high school, a middle school, elementary school, here, or another country? No, it doesn't tell us that. So just having one positive result is nice, and we can get a paper out of that potentially, but that doesn't stop there. Scientists dig deeper. They need to repeat this experiment with another group of students in another place to see if the same thing happens, because there is a chance, a small chance, that it could have just been a fluke. So we don't just, based on this, right, the evidence supports the theory, but it's not the end of it. In fact, let's just say that we did, by the way, running the research again is something we call replication. Repeating it with other people. Maybe we try it at middle school, we try it in a high school class, we try it in another state, another country, just to see. And if we get, 2, 3, 4 results that are all about the same, then we can generalize it and say this seems to be pretty universal. And that helps with the theory, but again, that's not the end of it. But going the other way, what if you don't get what you want? You find that those that studied on average got about a 38 out of 50, and those that didn't study on average got a 36 out of 50. 38 and 36 are not different enough from each other to say that there's a difference. So in that case, do we just scrap it? No, researchers dig deeper. A lot of times they will go back to their research design and say, did something else account for this? Did we not think about something? Or we go to revise the theory a little bit. In this case, we would probably say, well, maybe some of the students in the group that didn't study got caffeine, and that maybe improved their performance. So maybe we run the study again and we make sure that nobody has caffeine, because that could have been, caffeine is known to, increase a little bit of attention, learning, and memory because you're more alert and awake. So maybe that was something that could have contributed to this. So maybe we redo the experiment with different subjects, and try again. Going back to the green side, if the theory is, if the hypothesis is shown to be correct and those that studied did do better than those that didn't study, again, we're not there yet. If we were trying to revise the theory, maybe it's the 6 hours that's a problem. So maybe we make 4 groups instead of 2. 0 hours studying, 2 hours, 4 hours, 6 hours, and see if there's a huge difference between those groups. On this side, let's say that we did find that studying works. Well, the theory is not for an exam, right, necessarily. So there needs to be more. So let's say we're good. Studying shows that it works on an exam. So how do we take this further for this theory? Well, we can ask the questions, does studying help with a presentation? Does studying help with a paper like it does with an exam? Does studying help with group work? Because groups work together, but people maybe at different paces, at different levels. Would studying help a group assignment more than just the group coming together? Also, maybe it's the type of studying that matters. Some people just read the book and the notes. Some people highlight. Some people use flashcards. Some people take practice tests, right? Is one of those ways better than another? That could be the next portion or the next experiment to deal with this theory. Again, this just shows the theory data cycle, how it's cyclical, and that scientists dig deeper. So sometimes we may have competing hypotheses. Instead of saying those that study will do better, those that don't study will do worse, there may be two different theories that are competing with each other, and we can literally pit them against each other when we run an experiment. In the 1950s, a man named Harlow had an experiment, and there were others that had different theories. Harlow came up with the contact comfort theory. So what we see here in this picture is, on the left, is a wire quote-unquote monkey, a mama, that has a cylinder right here where you can see milk for the babies could be given out. On the right, you see a monkey that has more of a actual primate monkey face and doesn't look so much like a robot. And the body is covered in this terry cloth material, which is like the same material as a towel, to provide comfort and warmth and safety for the young monkey. So in this case, there were two different competing theories, and Harlow tested his against the other theory to show that we may be able to accept one theory and reject the other one. So Harlow's theory was the contact comfort theory. And by the way, after this chapter, below it, I have links and videos to other websites and to videos and things like this. So this Harlow experiment is the first one that's in that section. So after this chapter, it would be good if you guys watch this. And then after that, there's about a 19.5-minute John Oliver video from last week tonight about scientific research, which again, we'll get to towards the end. So I would recommend watching both of them after going through this. So the contact comfort theory was Harlow saying that the reason that monkeys cling to their mamas is because of that love, that warmth, and that safety from the outside world. Other theorists came up with the cupboard theory that says monkeys attach to their mama because mama has their milk. Mama has their food in order for them to survive and grow. So there was an easy way, Harlow said, for them to use the theory data cycle and test this. On the left is the wire monkey, does not look warm and comfy, but does have that thing you need to survive, food, the milk. So it's basically a robot milk dispenser. On the right is more of a mama figure, which is warm, soft, furry, and would be there if the baby needed love and protection and warmth and safety. So the contact comfort theory says that in this case, the baby would spend majority of its time with the cloth mama. The cupboard theory says the baby would spend most of its time with the wire monkey mama because of the food. And in this theory versus theory experiment, what we find, spoiler alert, from 70 years ago or so, is that the baby, in a number of situations, especially when actually frightened, goes to the terry cloth monkey. The baby does spend a few seconds, just enough time to get as much milk as it needs from the wire monkey, and then goes right back to the other one. So you can watch the video on this next time, or after this video. So scientists test theories. What the theory data cycle does for us is it helps us to give good scientific theories. What makes a good scientific theory? Well, that these theories are supported by the data In this case, the contact comfort theory was supported and the cupboard theory was not. The other thing that shows us is that theories can be falsifiable, which means it's a feature of a theory that allows you to be able to prove it wrong, at least under certain circumstances. And that is something that if you can't ever prove it wrong, right, there may be an issue with your theory. There is a saying that the simplest explanation is usually the best one. When we think of these really wordy and scientific and convoluted papers that people publish, you may expect, without, if you really don't know, you may expect that that the explanations they give for why things work or don't work can be very convoluted. A lot of times people that have conspiracy theories about things say, well, this specific thing shouldn't have gone that way, and why did it do this, and how could we have this, and blah, 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 blah. And it gets very convoluted, right? In scientific research, we actually look for simplicity. This is something we call parsimony. Parsimony says that all things being equal, all things considered, the simplest solution is usually the best. Why did the baby go to the terry cloth monkey? Because it was warm and comforting and safe. Yes, the baby needed food, but the baby spends more time with mama because mama is safe and loving. Why did studying work? If it did, because you actually retained more information and committed it to memory and learned more about it as you were studying, as opposed to seeing it once and then trying to figure it out. The other thing about good scientific theories, and you'll notice that I made sure to stay away from this word, is prove. They don't prove anything. You have the weight of the evidence. The terminology we use a lot of times is that studies suggest or studies support this theory or this, statement, but we never say prove. In psychology or really any science. Mathematics is different. Mathematics has proof. 2 plus 2 will always equal 4 in any alternate universe as well, I assume. So you can prove that. But even on a simple survey, if you were to ask people, which is better, In-N-Out or Five Guys, and you asked 100 people, there may be at least one person that doesn't agree that In-N-Out is way better than Five Guys, and that person is wrong, and that's okay, but that's their opinion, right? You're never going to get 100% of something. So we never use the word prove without getting 100% accuracy. There will always be at least 1% of people that are allergic to certain medications or vaccines. Does that mean vaccines cause autism? No, but that's another thing for another time, maybe a little later. Definitely in chapter 2, I'll probably bring it up, but let me get off my soapbox now. So even with the evidence strongly supporting even 99%, which again, that's even rare for a lot of things, we never prove anything. We always lend support to or suggest. So stay away from using the word prove or proof. Now, we talked about this idea of basic and applied problems. Well, the basic research, the basic approach is when you first have an idea or a theory and you're not even sure if that theory is valid until you test it. So, again, I will use the example here and the example of studying. We have heard that studying helps you to do better in class, but we need to know for that theory that this is correct. That's basic research. Basics, general, broad studying. Does studying help you do better on an exam? That would be the basic research. Here, way back in the day, there was an experiment where people had there's 3 hands. There are 2 hands and a rubber hand. You can see that the person is blindfolded. You can see that there is white noise in headphones, so they can't hear anything. And you see vibrations and fixation lights and things like that. The research question here is asking, under what conditions do people experience a rubber hand as their own? So at one point, this rubber hand, which is not theirs, is going to feel like it's their hand. It's tricking their brain. And if that happens, we take that basic problem and we can apply it to something very specific. So what does this rubber hand illusion have to do with anything? Well, if people can feel that a rubber hand is almost like their own, then what about people who've been amputated based on, diabetes, or maybe they got something blown off in a war, or some sort of bad flesh-eating bacteria that took a limb. When we apply this principle or this basic research to something specific, we can ask, based on this, which prosthetic hand design works best for your client to make it feel real, maybe so that you can control it, or that it tricks your brain into thinking that this is your real hand. That's where you apply it to something specific. In basic research, we're asking, does studying help you to do better on an exam? When we apply this very specifically, let's say that you're going to take the GRE, which is the SAT to get into graduate school. Should you take a GRE class? Should you get one of those standardized books? Do you just practice with practice tests online? Which one is going to get you the best possible score to put you in the best position to get into grad school? That would be the applied version of that. So the basic research is asking, does this theory work in general? And then you can apply it to something specific. And in between that, sometimes we have what's called translational research, which bridges the gap between basic and applied research and asks the question, can the lessons from this rubber hand illusion be applied to designing prosthetic hands? Then when we apply it, we say which of these prosthetics works the best, feels the most real, and makes the clients the most happy. So all of this points to scientists digging deeper, not just believing things at face value, looking at the empirical evidence, not just accepting one good result, not just giving up on one or two bad results. And let me tell you about the average that scientists say of successful experiments is probably close to 20%, which doesn't sound like much, but there's hope for the future, and we know not to give up. So, getting back to this idea of digging deeper, here we see the same girl in a picture, same background, everything's the same except for one thing. That's right, the color of her shirt. So, in an experiment, one group of people was shown, group of males was shown the girl in a blue shirt. The other group was shown the girl in a red shirt, and they were asked to rate her attractiveness. And if you think that the attractiveness was rated exactly the same, you'd be wrong. In this case, the red shirt was actually rated higher than the blue shirt. Did you guess that? Maybe it's because red is associated with hearts and love and Valentine's Day and all of that. So the color red seems to be at least slightly higher rated on attractiveness and things like that. But actually in academia, it's the opposite. As you'll see when we get into chapter 10 a little later down the road in the semester, the color red actually causes people's performance to be worse on academic things like math and anagrams and stuff like that, because most likely one of the explanations for that is whenever you got something wrong on a paper or a spelling test, all of your markings of what you got wrong were usually since elementary school really, in red pen. At least when I was going to school, that was the case. So there may be a sort of automatic implicit sort of response to red ink. So it's very interesting. But they dig deeper to find out why. They use empirical evidence. They dig deeper. Theory, data process, all of this to be a good producer of research and a good consumer. So finally, let's say we get our good experiment, we get our statistics to support and show a difference in what we predicted. Those who studied did better on an exam. Then scientists want to make this known. They want to make it public. So how do they share the results of their research with the scientific community? That's right. They find the journal that best fits their topic or theory, experiment, and they submit to it. And like I said earlier, it's not just, hey, here, I did this, and you should check it out, and you should print it. And the journal says, okay. No, there's an entire process for that. What is this process? From a manuscript, which is basically the final paper that you'll be writing in this class, it becomes a journal article. So first, it has to go through their journal editors, which may not have the specific technical knowledge, but they do the job that a regular editor would do for a manuscript or book or things like that, and check for spelling errors and context and grammar and things like that. And once that's all sorted out, then it goes to 3 peer reviewers, 2 of which are experts in your field, 1 of which is an expert just outside that. So since I got my degree in behavioral neuroscience, I was looking at genetics of schizophrenia, and my article went to 2 neuroscientists and 1 person in psychology that was not a neuroscientist. This way, the 2 experts can really look and see, did you use the right statistics? Did you have the right methods? Did you employ the right techniques? Was everything as technically sound as it should be for that field? The reason they have somebody from outside the field is because they want somebody with fresh eyes that isn't an expert in that specifics to see if there's something they didn't catch when they were looking for the very specific things. So the third reviewer is somebody that may not have the technical knowledge but understands the big picture and can sort of look at it through a different lens. And once those reviewers get through with it, they can reject it and say this isn't good. They can accept it, which it's almost never accepted on the first try. The most likely scenario is revision. They give it back to you with questions and say, you didn't address this, could you address that? Or maybe you should add this in your explanation, or maybe you should go back and do another experiment in this paper that shows this. So you go back and make your edits and do your changes, and then hopefully, eventually, it's accepted and you get published. Now, getting published is great, and you get recognition with your colleagues and people in the field, but when you want to get it known to the world, you can't just keep it in the scientific community. The scientific community is quite small compared to the rest of the world, so it has to be made public by journalists. There are both benefits and risks of journalism coverage. The benefit, of course, is that your actual message and your study gets out there into the world, and people are made aware of it, which could be really good. Think about, vaccinations for COVID that are going on right now. And all of these studies that are being done, of course, they're being reported on, and, who's winning the race? Are these good? What's going on with clinical trials? All of that stuff. Of course, there's also risks in journalism coverage because it's up to the journalist on how they want to report it. And as we all should know by now, some journalists have a lot of integrity and make sure to get things right and very technical. John Oliver is one of them. So you'll see the video that I'll make reference to in a minute. The journalist has to know, is the story important? Are they going to change it to make it sound more important? Is the story accurate? And the accurate point is really the point of contention. A lot of times it's like a game of telephone when you go from one person to the next trying to report what's happening. And it can really easily be lost in translation, especially if you're on a network like Fox News. So here is a horror story of what may happen, and oftentimes, this is where the John Oliver video comes in, oftentimes what does happen with a lot of research and publications, and this is a little insight into why. So it's kind of like my own little meme for your enjoyment. So we'll start here with the news cycle. Your research says, conclusion, A is correlated with B. Now, you should know that there's a difference between correlation and causation, and we're going to get to that in a second. Correlation means that the two things have a relationship with one another, but it has no basis for saying that one causes the other. One causing the other is not a correlation. So correlation, I have a saying, does not imply causation. Just because two things happen at the same time, or they may have a relationship, does not mean that one caused the other. Okay, back to this news cycle. So A is correlated with B, given C, assuming D, and under E conditions. So very specific. And they're not caused, they're related, they're correlated. So this is translated by your university PR office because they want their names to get out as well as your name because you work for them. For immediate release, scientists find potential link between A and B, and in the really fine print, under certain conditions. This is then picked up by a newswire organization or many, and here it gets morphed and translated into A causes B. Again, correlation does not imply causation. A causes B, say scientists, and then it's picked up by, oh no, the internets. Scientists out to kill us again? Here's all the comments. OMG, WTF, blah, 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 blah. Then, this is noticed by a local cable news station. We saw it on a blog, we must report it here. A causes B all the time. Oops. Sorry about that. A causes B all the time. Breaking news. Then goes to the local news stations. What you don't know about A can kill you. More at 11, because they want viewers to tune in. And here, eventually your grandma is wearing this tinfoil hat. I'm wearing this to ward off A, because A can happen and blah, blah, blah. And here you are with a facepalm going, no, this is what I reported. And then it gets turned into this at the end. And if you think this is far-fetched, it's really not. Does it happen all the time? No. Does it happen a lot more than it should? Absolutely. So again, you will hear this many times throughout the class and throughout psychology. Correlation does not imply causation. I will repeat this many times over the course of this class, course of this semester. Correlation means two things are related. Causation means that one thing caused another. So, in my very small version of this standing against anti-vaccinations, the first person who came up with this idea of vaccinations causing autism, based on a report, by the way, a publication that was later condemned and retracted, and the person who wrote that article, that journal article, based on 12 people, by the way, lost his medical license and is never allowed to practice medicine again because he admitted to making up the data. The first celebrity or person to speak out about this was Jenny McCarthy, who is the host of, I believe, The Masked Singer. My wife would be proud of me for knowing this. And she had her son vaccinated around 6 months of age. Well, let me tell you a little about this, just so you understand correlation versus causation. Nothing in a vaccine can cause your genetics to change. If you're a person that has autism, that happened before you were born because your genes coded for it. But the thing is that until your brain is developed enough, you're not going to see that there's any deficits that would be caused by the autism. So around 6 months of age is about the time that you would start seeing enough developmental progress to see if somebody was lacking something. Around 6 months of age is also when the first vaccinations come out. So the most likely explanation, if we're using parsimony, is that Jenny McCarthy got her son vaccinated about 6 months of age, and a short while later, maybe very short while later, he started showing deficits and signs of autism. So she made the connection, oh, it was because he got that vaccination. And so she's saying that the vaccination caused the autism. What the most likely explanation is scientifically is that she vaccinated her child around the same time that he would start showing delays and deficits, and she attributed that to the vaccinations. So again, correlation does not imply causation. It would be like the same example, a little different, but pretty much the same. If you've never been to California, you've never been to the beach, and you first come to California, you're really excited, you go to the beach, and you get in the water, and ow, you get stung by a jellyfish. So you quickly run away and go away from the beach, and you call, text, post on social media to anybody and everybody, don't go to the beach. You will get stung by a jellyfish. Now that sounds ridiculous, and the chances of that happening are very, very slim to almost none. And yet, it's the same argument. Correlation, I went to the beach, I got stung by a jellyfish, so don't go to the beach or you'll get stung by a jellyfish, despite all the empirical evidence against that. Correlation does not imply causation. Thank you very much. And I will talk to you very, very soon.